Welcome to Pulsafeeder Engineered Products channel for this brief tutorial to generally size an external gear pump. Efficient operation of chemical processing pumps requires proper pump selection. To correctly size a pump, you will need to know some critical information. The Pulsafeeder family of external gear pumps includes the magnetically driven, sealless, non-metallic Eclipse and metallic Isochem product lines, as well as the Eco mechanically sealed product line. The differential pressure of the Eclipse pumps is 150 psig, while the Isochem and the Eco pumps have differential pressure limitations of 100 psig. Eclipse has flow ranges from 0.45 gallons per minute up to 33 gallons per minute. And the Isochem and Eco flow ranges are from 0.75 gallons per minute to 55 gallons per minute. The temperature range of the metal pumps is negative 100 degrees Fahrenheit up to 450 degrees Fahrenheit. The non-metallic Eclipse covers a temperature range up to 200 degrees Fahrenheit. Temperature is an important factor because external gear pumps have very close tolerances, and elevated temperatures create thermal expansion, which reduce those clearances. If the expansion becomes too great, it will result in excessive wear. Viscosity generally decreases with an increase in temperature. The maximum viscosity for Pulsafeeder external gear pumps is up to 100,000 centipoise. The maximum solids that these pumps can handle is up to 70 microns and at a concentration of 10%. It is absolutely recommended that a 200 mesh screen strainer is supplied for all gear pump applications. This tutorial covers general sizing and pump selection. In another tutorial, we will select actual materials of construction, so be sure you locate a reliable liquids directory to determine material compatibility. It's Pulsafeeder policy that the end user is responsible for determining if the materials construction are suitable for their particular application. And in another tutorial, we will also discuss NPSH, net positive suction head. The customer is responsible for making sure the suction conditions are adequate for a proper pump operation. Differential pressure is the algebraic difference between suction pressure and discharge pressure. The curves we'll be using in this example will be in terms of kilopascals and pounds per square inch, or PSI, and you will need to determine the differential pressure between the inlet side and the outlet side of your pump in terms of these units. So suction pressure is the average pressure measured at the inlet port of the pump, and discharge pressure is the average pressure measured at the outlet port of the pump. Differential pressure is the algebraic difference between suction pressure and discharge pressure. And the differential pressure directly relates to the power requirement of the pump. For this application, let's consider an application of sodium hydroxide, or also known as caustic soda. For this application, it will be a 1 gallon per minute requirement at a 50 psi differential pressure. The temperature will be near 68 degrees Fahrenheit. Could be up to 90 degrees Fahrenheit and down to 40 degrees Fahrenheit. The viscosity of this product is 1 centipoise. It does not crystallize in a closed system such as a magnetically driven pump, and it's compatible with 3/16 stainless steel and PVDF. Once the pump is selected, we need to make sure we check the ratings of net positive suction head required for this pump. So let's assume that we have determined that the required pump family is the Isochem metallic sealless magnetically driven product, and that the model GMC2 seems to be the closest model that could fit the application. Let's examine the GMC2 performance curve available at the Pulsafeeder website to determine if this is a correct fit from the standpoint of flow and pressure. First, we identify the required level of flow on the left-hand side, so let's mark that. across the graph. And then from the bottom of the graph, let's draw a line up from the pressure we'll be operating at. We can see that these lines intersect at just about 1440 RPM, and that's the required RPM of the pump for this flow and pressure. From the line we drew for pressure, follow that line down to where that intersects with the 1440 RPM curve. Then let's follow over to the right hand side and see where that intersects with the required brake horsepower. We fall right at about 0.12 brake horsepower, so a 1500 RPM 1/4 horsepower motor should be fine. But if you want to select a motor that will give you the proper operation up to the maximum rated pressure of this pump, you can follow that 1440 RPM curve all the way out to the end, and it goes just over 0.2 brake horsepower, so you might want to consider a motor that's maybe one frame size higher than what we've selected here. Well, we hope this was a valuable tutorial for you. If you have ideas for other videos or tutorials you would like to see from us, be sure to subscribe to our channel and send us a note with a suggestion. Thank you for spending a few minutes with us today.